Thank you very much. All right. Yesterday I had two adventures in my life. First is starting to be part of this team and attending this conference. And the second one was at night. I tried to go home on foot, and then I lost in the city. And it took me approximately 2 hours to get home. And it's not a problem. My presentation is approximately the same. I built an antenna once in my life, and it wasn't working. And then I built another one and the filter, and it got better, better, and better. As last night I get closer and closer to home. So my newest ground station is located in Szeged, at the top of my university, and it's look like this. It has two 𝗖𝗁𝗁 antennas. It's not very tall. That's me, and that's a student. I think he was programming the rotator control algorithms. This whole station was designed by a student. 4 or 5 students were involved in this spring. These are 𝗖𝗁𝗁 antennas, 10-element ones. They are commercial antennas, nothing special. You can buy them if you search for CDMA antennas, because they made lots of them for 450 megahertz band. But they have no use now, except you use it for LTE 450, but they are perfect for radio amateur band also. So what about the hardware layout of my station? I have 2 antennas and 2 reception paths. First, on channel B, I have a cavity filter. It's self-made. I show you some slides of it. I have surface acoustic wave filters, and then mini circuits low noise amplifier. And then I save the recordings coherently by a bleed RF module. Here is the cavity filter. I tried to buy one. It's quite expensive. It's so expensive. So one day I woke up and said, let's build one. It's not that difficult. Basically, it's a tube, a rectangle tube. Inside that, it's another tube. So easy. I turned on YouTube and asked my colleagues how to use a lathe pad, and they showed me how to turn rods. And I made this. I thread cutted the end of the rods so they can fit in this plane. For those works, I used the dead ends on the lathe pad, and then it was finished. And what about its result? I measured it with a calibrated network analyzer, and here is the transfer function. You see the peaks. These are the harmonics of the resonant circuits inside the cavity box. And here we see quite a big attenuation. It's good. This is the band where broadcast television is in the air. And since the station is 1 kilometer away from a transmitter tower transmitting more kilowatts of power to the air, we have to use a filter like this to suppress these signals. And nonlinear effects won't reject my reception. But what about the main lobe? I want to receive my signals. Here is the bandwidth of the filter. It's quite big. If you can read, and I can read, it's more than 150 megahertz. It's It's not very good, but it has some advantages. For example, I wasn't to simulate or measure the effects of outside temperatures on the resonant frequency. But on the other side, it turned out to be very good because the insertion loss of my filter turned out less than half decibels. It was quite amazing and interesting. It works like a charm. Yeah, so about software. Yeah, here is the antenna next to my slide. And first, I use a fractional mixer. Why do I use this method? Because I oversample the data. I turn the intermediate frequency filter of the software-defined radio to the smallest bandwidth. It's 200 kilohertz, if I'm right, but sample the data with 1 megahertz. Why? Because there are strong stations around me. These are Yagi antennas, and they have many side lobes. And the side lobes may point to amateur radio stations transmitting in the 70 centimeters band, for example, radio repeaters and so on, even short-range devices at 433 megahertz. And I tune the radio. So here is the center frequency. And these other stations, although they are attenuated by the filters, especially the last intermediate frequency filter, they'll alias to somewhere. And I tuned my radio so the aliases won't disrupt my signal. And then the attenuated and not overlapping aliases I suppressed by a filter. Before that, the real center frequency is set by a fractional mixer. Then I decimate the signals, so I optimize on the CPU usage in the later processes. Then I do a Doppler correction, other filter mechanisms, decimate again, and write the file to the disk. To control my reception set, I use the gpredict. It downloads the TLA files, and there are two protocols which can communicate on. It communicates with the rod control daemon, and it turns my rotator. It is a basic ISO G55001, and it communicates via rig control protocol, and sets the Doppler corrector to the current frequency. It uses a phase accumulating mixer. So it corrects the Doppler shift of the received satellites. And it also controls when to start writing a file to the disk and when to stop writing to that file. And it turned out to be working. There were several iterations, and these are the last block diagrams we are using right now. As you may notice, we have two antennas. They are placed in a different polarization. So one is horizontal, one is vertical. What could be the advantage of this system? We have two observations, two independent observations of the radio signals. For example, let's suppose there is some jamming on the frequency. I tracked the MRC-100 satellite, and right now I'm also tracking MRC-100 satellite automatically at home. And unfortunately, its frequency is the same as the frequency of the audio band of one community TV channel. And when there is some leakage from the cable TV, you may receive it. But sometimes these jammings only appear on one one antenna, so on the other you can still receive the signal. It's good. This was the first point of polarity diverse receiving these signals. But I went further and started to try out algorithms to improve the signal even more. I have two observations, and how can I get more CRC correct packages out of my signals, out of my recordings. And then I tried out some linear and nonlinear methods, and yeah, it worked like a charm. And I wrote the manuscript and sent it to IEEE, and that's how this presentation stops at the copyright wall, because IEEE said I cannot presentate figures from the manuscript. So I created other figures and blurred some labels on it, so I can show you what I have achieved. Here you can't see, and I hope you can see, the name of the methods I used. This will be available on IEEE in weeks, if I hope. Here you can see two bars. One represents number of pockets received from one antenna, and this one represents the number of pockets received from the other antenna. And these other ones are nonlinear methods and nonlinear filters, averaging, or not averaging, so calculating a new virtual channel, which is then demodulated. And you may see that on this channel, I can demodulate many more packets than on this or this one. But there may be an overlap. So if I add this one and then this one, it's much higher than this one. It was a pain to create figures for such distinguishing. I had 10 methods, I had many recordings, and it took days to figure out how to show anyone what I have achieved, or even show myself what I have achieved. So then I decided to create correlograms. Correlograms, yeah, there should be labels in this line, and to plot two methods and the relation of them, I used the bit error ratio. So I took one pocket, demodulated by both the methods, and scatter plot the bit error ratio of one and the bit error ratio of another one. So you may see that between this method and this method, the bit error ratio increased by this method. It's always less on this method. So this method is better than this one, but a few exceptions. Yeah, there are meaningful correlograms here. Maybe I should show you this one. So the bit error rate of this demodulated by the same pocket on this method and this method is nearly the same. The correlation between is 0.945, which is quite good. There are even bigger correlations here. It means that the two methods are the same. They have the same quality when creating the new virtual channel, which we will run the demodulation algorithm on. This is some kind of heat map. Every column is a packet I found in my recordings, and every row is a method. You see, these packets are found on all the methods, all the virtual channels, and so on. But there are exceptions. For example, these ones were only found on via these methods and these methods. And here are the interesting ones, because the raw data are somewhere here and here. These packets were only found by using these nonlinear filter algorithms. This is anyway called a heat map. The brighter one point, the more the bit error ratio. And there is a great function in R programming language which reorders all the data. So it's a so nice figure because a clustering algorithm switched the order of the packets and the order of the methods. So the similar packets go next to each other. And as a side channel, you may see a dendrogram here. And this dendrogram shows a relation between these nonlinear averaging algorithms and nonlinear filters. Yeah, that's all. And finally, I end up with a Venn diagram. The colors are not very bright, but here is a circle showing packets demodulated only on the channels with no nonlinear preprocessing step. And you see there are 7 packets only being to be demodulated without any algorithm. So applying anything would distort these packets, and you end up unable to demodulate it. And what about the others? There is a method A, for example, which was uniquely demodulating 48 packets. Only this method was able to find these packets. There are other packets, for example, these 3,469, which were decoded by all the methods. But let's not talk about them. Let's talk about the ones that are outside this circle, so the ones unable to be found on signal channel methods. And what are these numbers? On the unprocessed recording data, I was able to find 3,819 packets from MRC 100. What about with the nonlinear filtering methods? I end up with 4,248 packets. And what's the difference? The difference is approximately 600, which is approximately 16% increase related to just using the raw recording of yours. And yeah, I think it's a big thing. I haven't improved my ground station. It's only a software thing. And some of the algorithms even work on single channel recordings without polarity diversity. So yeah, that's my work. Yesterday morning, someone said that we all want more data from the satellites. And here are, and at the same time, aren't the methods on my slides, how to do them. And I hope IEEE publish my manuscript soon, so all of you can read it. So stay tuned to IEEE. And this is the end of my presentation.
Does anyone have any questions? Okay, Tibor.
Great talk, thanks for improving our data. So my question is, does your process, signal processing, include phase shifting, adding phase shift to the different polarization receptions and improving the signal to noise ratio by adding the 2 channels in a correct phase?
Yeah, that's so that's a linear method, and I do that, and It is, if I'm right, this row maybe. So it's more, but it misses packets.
But it's included in the other nonlinear.
It's included, yeah.
Okay, and the other question is, let's go back to the bars, the bar chart and tables. This one. So what we see here is the number of demodulated packets, right? Based
Right.
on the different methods.
Right.
Including the linear methods.
Yeah, I think they are here and here. So the first three ones, if I'm right.
Four methods are the normal methods, and the 6 other are your.
Non-linear ones, yeah.
Okay, so the best ones are the tallest ones, the 6th.
It depends on what you call best ones. I call a best one, personally, which finds packets uniquely. No other methods find. It doesn't matter if I show a method which finds every packet and one more than when you see a raw recording. A good method is a method which finds you new packets and a huge number of new packets.
Did you check the contents of these packets, the unique packets?
Not yet. I have uploaded it to your server, and your server said that it's accepted.
Great job.
So we're going to take one more question. Anyone else want to ask something?
But if you...
Okay. So, thank you, Adam.